topic today is what the hell are we doing as a junior company in the core imaging business, and I guess basically what I want to try to demonstrate to you today is that you can see the cartoon. We're not kind of following the herd, and I think eventually the herd's going to catch up to us. So let's see if I get the buttons right here. The typical disclaimer, mine's not quite as nice as Doug's was, but I have to maybe get that one. So why are we doing core scan? Really to eliminate the inconsistency of geologists. I'm a field geologist, but the reality is geologists are very inconsistent, and this creates a lot of downstream problems. Some of the minerals, I don't care how much experience you have, they're very difficult, if not impossible, to detect with a naked eye or a hand lens, and core scan eliminates that to a certain degree. We're also able to systematically define textural and temporal relationships of some of these complex mineral assemblages, which ASD cannot do. And so that's also a very important aspect of this. We're also able to determine chemistry and crystallinity, and we had some very good talks this morning that discussed the chemistry of micas, and we would agree wholeheartedly with that. Value in determining vectors to mineralization. Most people think that this is an exploration vectoring tool. It is, but that's not one of the main reasons why we as a junior company decided to do it. We actually collect geotechnical information, but really where we think the big value add is that we want to create a project where we have systematic mineralogical data, especially the clays and micas, that have potential repercussions in downstream activities, such as mining, blasting, slope stability, crushing, grinding, metallurgical processing, and tailings and waste disposal, acid drainage issues, okay? And providing that as an upfront early in the project, as opposed to waiting till we've already spent $2 billion on a plant and find out it doesn't work. So just a little bit about core scan. I don't know if I'm robbing some of the ladies' parts of their talk, but basically there's 12 labs located throughout the world. Regulus is the only junior company in the world that has using a dedicated lab for their project. Not that we want to try to be the leading edge of the technology, it just happened to work out that way. And we have our lab located, you can see in green there, in Cajamarca, Peru, which by the way was the first lab that was brought into Peru, although there's now a second lab being located into Arequipa. This is a picture of our core facility, and you can see the tucked away in the back so that they don't bother us. There are the core scan people over here. You can see the lab, and we are scanning all of our historical core plus new. To this point, we've scanned over 35,000 meters of core, 75 drill holes, and it's one of the only few projects in the world, really, where we're scanning all the holes for a complete project. A lot of projects, they're doing selective scanning, but we're scanning everything. So we're in the land of Peruvian giants. Antucory is located here in northern Peru, right next to the producing Tantuatay mine, 6 kilometers from Cerro Corona, and also near about 45-minute drive from Yanacocha. So we're in elephant country. Just a quick bird's eye view from Google Earth. You can see our project here in the pink and red claims. We also have an option joint venture agreement to acquire 70% interest in the yellow claims. And the green area here is a collaborative data sharing agreement we have with the Coimolache joint venture in the mine next door. And you can see 6 kilometers away here, Cerro Corona. So we're in a fairly well-developed, from a mining point of view, area. Just a quick overview of the geology. I don't want to go into too much detail here, but effectively what we've got, this is a cartoon cross-section. We've got Miocene volcanic rocks shown here in the various shades of pink. Those are unconformably overlying Cretaceous sedimentary rocks, the limestones in blue, calcareous siltstones in brown, quartzites in gray, and those are intruded by a bunch of pre-unconformity porphyries and breccias, and then other intrusions that are post-unconformity and breccias that are related to the high sulfidation system. We can cartoonify this, that we've got four main different styles of mineralization. We've got an upper area here of high sulfidation style mineralization, copper, gold, silver. We've got a lower area here where we see skarn style mineralization, copper, gold, silver, and base metals. And then deeper down, we're starting to see indications of copper, gold, moly, although we're starting to see laterally indications of the same. And I think tomorrow afternoon, Hubert Gamarra has a talk, and we'll discuss this in more detail in the project showcase. And then this is overprinted by lead, zinc, base metal carbonate. So we've got four mineralizing events all bringing in copper and gold. So a very complex system mineralogically and alteration and obviously the sulfides. And so this was one of the reasons why we elected to go full on with the core scan. We're currently analyzing close to 40 minerals, which I think is probably one of the largest libraries that's being done by core scan worldwide. Because of the complexity of the overprinting mineralization. And in the subsequent slides, just to show you, we're going to show you some correlations here. The orange is greater than 0.6 copper or 0.6 gold, and the reds are 0.8 to 1%, and magenta is greater than 1%, just so that you have an idea what the colors mean, because you won't be able to see legends on the subsequent slides. So just a couple of quick examples of how we're using this technology. Here you can see the drill hole down here. Here you can see the copper, the gold and the copper grades. And one of the things at that unconformity, not only is it unconformity, but it's also a paleo weathering horizon. And what we can see here is that we can see the pyrophyllite and kaolinite of the high sulfidation event abruptly ends, and we get the continuation of white micas, but the white micas are more intense. And we also start to see the development of smectites, or in this case, montmorillonite, and a little bit of gypsum kicking in, and then iron oxides. And then at this line, we see another abrupt change, and that's basically the sulfate front, or the gypsum front. And you can see here the anhydrite veins, and you can see the intense development of gypsum right at that contact. Okay? So this, you can imagine when we have this in all the drill holes, we can start to model this in 3D. And this has big implications for characterizing the ore when it comes time to for metallurgical studies. Here's another example of skarn zonation and overprinting. You can see here, I don't know if you can read these very well, but basically we've got white micas. We can do the crystallinity and the compositions. We can see a zone in here where there's very little white micas, but we start to see the prevalence of Vesuvianite, which is a common skarn mineral, which is not easy to identify with a hand lens. We see it associated with clinochlor and also with chlorite here. And then as we go deeper, we start to see epidote coming in. But you can see how you can pick off these very, very sharp boundaries. And you can imagine when we start to model this in 3 dimensions, it's going to create a much more complete story than just traditional visual logging, which we, by the way, still do very detailed visual alteration logs, because this is not a replacement for logging. We can also see in this case where it's interesting, this morning people were talking about this chlorite sericite type alteration. At Antiquori, we also see a late overprinting event that's bringing in very strong white micas associated with anhydrite. In this case, it shows as gypsum because the core scan can't distinguish gypsum from anhydrite, but this is anhydrite. And you can see this zone, and you can see the gold and copper grades here. The highest grades are associated with the most intense sericitic overprint here. Another example where we can see more transitional stuff, where again we can pick out very sharp boundaries, a little zone through here, where we can see the copper grades here very high, strongly associated. In this case, this is up in the high sulfidation environment, where we're seeing pyrophyllite with diaspore associated with the high grades. So not all the high-grade copper and gold is associated with the same mineral assemblage, and this really helps us to distinguish on a very, very detailed way where the boundaries are for our mineral domaining and eventually for metallurgical test work. Here's another example where we can actually map out transitions, where we see an inner zone here of very high-grade copper and gold, and it's associated with diaspore, a little bit of dickite, kaolinite, and porphyroite, and then you can see it transitions out where we start now picking up white micas on the boundaries in a transition zone, and then we go out basically into much stronger white micas, and the grades correspondingly drop out. So not all white mica is associated with high grades. One of the things that we found with the core scan that was quite interesting is that in some of the early deeper drilling we did, we encountered within the quartzite package, we found arcosic sandstone interbeds, and they had this very distinctive brown coloration, which for me, I thought it was like a biotite hornfelsing style of metamorphic contact metamorphism, as did some of our other senior geos. However, when we core scanned it, it actually came back as being porphyroite with muscovite illite. And so, just being the way stubborn guy I am, I didn't believe that, so we sent it away for petrographic work, and lo and behold, yes, it does come back as being white mica, but also has andalusite associated with it with quartz. So that was interesting, but not even believing the petrography work, just to make 150% sure, we sent it away for XRD, and the XRD results came back exactly the same. And so basically, what this told us was, I think, a very important observation, and that is that there's two ways, and now just recently in Salta at the IAGOD meeting, Jeff Hedenquist now says there's 4 ways you can do this, but we'll keep it simple today and say there's 2 principal ways to form porphyroite. There's the standard vapor condensation in the advanced argillic lithocap, so high up in the system. We see porphyroite like that associated with the Miocene high sulfidation style mineralization we have. But where we're seeing this style of alteration is down deep, some cases down at sort of 600 to 1,000 meters depth, and it's clearly got a different association. And this can be explained by just simple fluid cooling. I'm glad I'm not the first guy to show this phase diagram. Thanks, Klaus, for showing that diagram this morning. But basically, all you need to do is take your fluid that has a potassic composition here. Normal path is to cool it down through here, so you get the cericitic or the dreaded philic word, and then eventually into the advanced argillic. But a slight shift in the acidity of this fluid, and you can come down through the andalusite porphyroite field, and that's exactly what we think is going on at Antiquaria at depth. So, now the more business side of things. Why are we doing this? This is a slide I took from Regina Baumgartner in a talk that she gave back in 2012, showing the value chain. And we all, I think, understand the value chain, but what I think is missed in a lot of cases is that this part, we're good at, as explorationists, we can discover the mineralization. And then when it comes to characterizing the ore body, this is where I think things potentially go off the rails. Because the quality of the work that we do at this stage in the chain affects all the rest of this. So if this is done poorly or incompletely, all the rest of this potentially suffers. And I think that's why, engineers, how many engineers do we have here today? Nobody wants to claim they're an engineer. But engineers, when things go well at an operation, they always claim that it was because of what they've done. But the minute there's a screw up, the first word that comes out of their mouth is bloody geologists, okay? And it's typically because somebody didn't do their homework properly at this stage. So we really need to focus on this part of the process. So I don't expect you to read all the details, but we have a very complete flow sheet work pattern that we do with every piece of core that comes into our facility. And a big part of this workflow sheet is the core scan data collection. And we also do a lot of systematic petrographic work, both in reflected and transmitted light, and we do 4-acid digestion, multi-element geochemistry on every meter of core that comes through our facility. And so we can then take all of the analysis from the petrography, the analysis from core scan, integrate it with our lithologic alteration and mineralization 3D models that we're developing in Leapfrog, And from those, we can then put those into, help us to better define our 43-101 mineral resource. And this can help us to define very well-defined domains where we can then focus our metallurgical test work. I've seen so many projects where people rush to do metallurgical work, spend a lot of money doing it, and they end up spending probably a large chunk of their budget doing this metallurgical work on rocks that only really represent 5% of the ore body, and therefore basically useless work in the long run. So it's much better to have a good understanding of what the metallurgical work's going to be on and that it's representative of the deposit. And the goal is to really develop a geometallurgical model. A lot of the big companies are onto this, but we as a junior company believe it's important to come up with something, because at the end of the day, our business model isn't to put this into production, it's to sell it to somebody. And the better we can present them with data that they can have confidence in making their decision and not having to repeat work, I think adds value to the project and potentially the sale price, which is, of course, of great interest to our shareholders and management as well. And then obviously this all goes towards the PEA to see whether this is actually going to be something that's economic. So, data integration, I think this is all pretty straightforward stuff. Integrating all our geologic models. We are producing somewhere in the neighborhood of probably close to 20 or 25 different models that will be incorporated into this, ranging from obviously lithology alterations, but also different elements, geochemical, our multi-element geochemical data, all of our petrographic data, our resource model, and everything will go into this, so we can actually, and our core scan data is a big part of this as well, where we can plug the core scan data in and basically characterize each block in our block model. So, can this type of work really benefit us in a mining operation? Here's the ways. Again, exploration is the way we think of it, but really what I'd like to try to leave you with is that it's got a lot more applications downstream than I think some of us might take into account. We can start to use this as an early reflection of relative hardness, potentially using it integrated to look at the bond work indexes and mill throughputs, to get an idea if we're dealing with rocks that are dominantly going to be hard with a lot of quartz and feldspar, or whether they're going to be soft with a lot of phyllosilicates. Sulfides, we're going to need to know. I mean, when we start to do our early metallurgical tests, if we don't get good recoveries, why is that? Is it because maybe we've got problems with clay mineralogy or micas? So we'll have a better idea of what the potential culprits are if we're not getting recoveries that we need. If the ore goes to the heap leach, we need to know, if rock goes to the heap leach pads, we need to know potentially what clays and micas are in there that it might be clogging up the works before we start putting stuff on the pads. This will also, I think, we'll be able to show, also use this in where the proposed pit wall angles are. Do we have a lot of clays that aren't going to be able to support steep pit walls? So it has implications with stability, etc. And then this will also allow us to do more predictive things early on in the timeline of a project, so that we don't spend $2.5 or $5 billion on a project and find out that we messed up and don't understand the mineralogy properly. So the future value add, geometallurgical studies are, I think, the future. I think people are onto this, so this is not new news. But it's really integrating a lot of things, and we're doing this at the junior company level. I don't know how many other junior companies are doing this sort of work, but we put ourselves in the shoes of a major company, because that's eventually who we want to try to sell our projects to, and we want to provide them with a project that satisfies their needs of what they think they need. And so we're trying to do that early stage. This is obviously integration, like I mentioned, of a lot of different data sets. And I think that this one model that we create can be used by different people. The exploration geologist can use it for targeting, mining engineers for drilling and blasting, geotech engineers for their pit wall and underground development, process engineers for the grinding and crushing, metallurgists for the flotation or the leach pad characteristics, the environmental people for the acid mine drainage and waste management, and also helping in things like scheduling, blending, and eventually even the concentrates and smelting. So overall for us, it's a value add to any future buyer of the project and adds to the project's NPV as far as we're concerned. So one of the big criticisms I always hear about CoreScan from people is, and I'm not a salesman for CoreScan, although maybe I should get on the payroll, is there's too much data. What the hell do we do with all this data? Okay? And yes, CoreScan does produce a lot of data. However, most of the heavy data and the processing is done on CoreScan supercomputers in Australia. The data is stored on their servers and is backed up on a regular basis. So you don't have to have this trillions and trillions of gigabytes stored on your laptop. Okay? Data can be composited in whatever intervals you want to use. People say, oh, well, it's way too detailed. You know, we don't need all that detail. Well, then you don't have to use it. You can composite it. So, for instance, we're compositing our data to our assay interval. So then we can directly see what that assay interval looks like in terms of the mineralogy. And we also do it at our resource model block size, so 10 by 10 by 10. But we also still use the detailed data for other more specific tasks. And there's various ways you can use the data. Visually, obviously, that's the one that everybody's probably most familiar with, you know, the nice pretty colored images. Those are really great. You can see a lot of spatial relationships, and again, that's the advantage over the ASD. But there's also a lot of hard numerical data. That's I call the non-sexy backbone behind all this that can be also available for analysis. And that's really where the real power in this actually comes from. So the other thing I always hear is it's too expensive, okay? And, you know, great idea, but yeah, it's too expensive. It's going to chew up all our budget. But, you know, what I say to that is, well, it doesn't cost as much as those last two dead drill holes you guys drilled. And so anything that can help us to better target and better take advantage of understanding of the system helps us in better allocating our drill targeting budget. So roughly we're paying, and I'm not sure if I'm supposed to show this, but you know, it's roughly between $20 and $25 a meter. So you know, we're paying close to $700,000. Sounds like a big amount of money, but one 1,000 meter drill hole in our project costs close to $500,000. So I only have to screw up one drill hole, and I've paid for all that core scanning. Okay. So, although it's initially an exploration targeting vectoring tool, I really do believe that the true power may lay in its downstream applications. The idea for me is to bring forward and realize something closer to a true processing variability and its inherent risk and opportunity. So basically, what are the potential fatal flaws that we might face with this project, and know those sooner than later? Early identification of those risks really, I think, has a big impact, not only for us, but also for potential buyers, and produces much more robust project economics. Obviously, integrating this with good geochemical data, and this allows us to, like I mentioned earlier, really target better areas for exploration, but also help with potential future mining, processing, waste management problems that we need to solve. So, to finish, really integration of hyperspectral scanning into the workflow of an advanced stage exploration project for us is a no-brainer. And I wouldn't recommend that we're going to go out and do this on every project we have, because it's just not cost effective. But in a project like this, where we know that this is going to be a mine someday, it's worth the investment. Thank you.